All right, today we're going to be wrapping up Chapter 5. We're looking at Section 5.5, which is about the Fibonacci sequence and the golden ratio. This is sort of a shorter section than what we've dealt with before in Chapter 5, and there's really not much in the way of examples that we're going to look at. I think there's just one example in the whole thing. Really, this is kind of a very brief overview of this very famous sequence of numbers, the Fibonacci sequence, and the golden ratio is something that we can derive from that sequence. In math, we talk about sequences a lot. It's a major topic in calculus too, although we don't need any calculus to be able to talk about this, what we're talking about right now. A sequence, for our purposes, you can just think of it as an infinite list of numbers. In this case, an infinite list of natural numbers. And oftentimes those sequences have some sort of pattern that defines them. The Fibonacci sequence is one such sequence, and the reason we're looking at it here is because it has a number of really interesting properties, and it sort of encapsulates some interesting things that turn up in nature. So first of all, let's talk about who Fibonacci is. Fibonacci, or Leonardo of Pisa, was his name, first wrote about this sequence back in 1202, so a really long time ago, and it turns up as the solution of a problem that he poses. Your book will talk about that problem. We're not too interested in that here. What we want to look at is how the sequence is defined. So here's the first few terms of this sequence: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and it keeps going. It continues. The next term in the sequence would be 89. Where are these numbers coming from? How do we define this sequence? Well, the first two numbers are just defined to be 1. They don't come from anywhere specific. We just say let the first two terms be a 1. Starting from the third term, we can see the pattern emerging. So this third term in our sequence, this third number in our sequence 2, comes from the sum of the previous two terms. 2 is equal to 1 plus 1. And then each term in the sequence after that, it follows the same pattern. Each new term comes from the sum of the previous 2. So 3 is equal to 2 plus 1. 5 is equal to 3 plus 2. 8 is equal to 5 plus 3, and so on and so forth. And this generates this infinite sequence of terms. Now, when we talk about sequences in math, there's some terminology that we use. One such term that shows up here is what we call a recursive formula. Now, a recursive formula is one way of describing a pattern that might be apparent in a sequence like this one. Basically, it says that if we know, or if we want to find the next term in a sequence, a recursive formula tells us how to use one or more of the previous terms to create that new term. So the recursive formula that defines the Fibonacci sequence is shown right here. Now, in order to understand this terminology, one important thing to know is that we, sorry, this is actually incorrect. That should be a 1 right there. One important thing to know is that the general, if we want to talk about a general term in the Fibonacci sequence, we use this symbol right here, capital F with a subscript, and the subscript is going to denote which term in the sequence we're talking about. So F1 would be the first term in the Fibonacci sequence. F1 is equal to 1. F5 would be the fifth term in the Fibonacci sequence. It turns out that the fifth term happens to be a 5. That's coincidental. If I wanted to talk about F10, I would be looking at the 10th term in the sequence. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I could say that F10 is 55. Okay? So the way that we could define a recursive formula to generate this Fibonacci sequence is we start by defining F1 and F2 to both equal 1. Which is what we're seeing here. And then we know that after that second term, a pattern emerges that uses previous terms in the sequence. So what we say is whenever n is greater than or equal to 3, meaning we're looking at terms from the third position or onward, Fn, so the nth term in this sequence, is equal to the sum of Fn minus 2 plus Fn minus 1. N minus 2 and n minus 1 are going to denote the positions of the terms, the two terms that come before Fn. So this is saying that each new term in the sequence is equal to the sum of the two terms that come before it. Okay? So that's how we get this thing that we call the Fibonacci sequence. Now, like I said at the beginning of the video, there's a number of interesting properties that occur with the Fibonacci sequence, one of which we can look at right here. So we could state this as a theorem or just a simple fact. It says that the sum of the first n terms, some of the first, this is stated incorrectly, the sum of the first n squares of the terms of the Fibonacci sequence is always equal to fn times fn plus 1. So a little typo here, but basically what we're saying is if we take the first n, and n can be any number denoting any position in the sequence, and square all of the terms up to that nth term, add them up, the result is always going to be equal to the nth term times the term that comes after it. So let me investigate this for a second. This is the one example we're looking at here. Confirm this property that we described here for n equals 1 through 5. So when n equals 1, then we're only looking at the first term in the sequence, f1, and we're squaring it. That's equal to 1 squared, which equals 1. But 1 is equal to 1 times 1, which is the first term times the second term. That confirms this property for n equals 1. Now, if n is equal to 2, I'm adding up the sum of the squares of the first two terms in the Fibonacci sequence. So that's, remember, f1 is equal to 1. You can see the sequence up here. It's equal to 1. f2 is also equal to 1. So this is equal to 1 squared plus 1 squared. Of course, 1 squared plus 1 squared is the same as 1 plus 1, which equals 2. Okay? And what this is saying is we want to show that this is equal to f2 times f3, which is 1 times 2, and that's true. Okay? Let's confirm this now for n equals 3. So I want to sum the squares of the first three terms in the Fibonacci sequence. That's 1 squared plus 1 squared plus 2 squared. I squared the first three terms in the Fibonacci sequence. This is equal to 1 plus 1 plus 4, which is 6. Okay? And remember, we want to show that that's equal to the third term times the fourth term. Well, the third term is 2, and the fourth term is 3. And that is equal to 6 when we multiply those. That's equal to f3 times f4. Okay? Two more cases to look at. If n is equal to 4, that's the sum of the first four squares of terms in the Fibonacci sequence. f3 squared plus f4 squared. This is equal to 1 squared plus 1 squared plus 2 squared plus 3 squared. So that's 1 plus... We already know that this adds up to 6 from the previous example. 3 squared is 9, and 6 plus 9 is 15. Okay? 15 is equal to 3 times 5, which is the product of the fourth and fifth terms in the sequence, which is what we wanted to show would happen. Okay? Now I need to do this for the final case of n equals 5. So f1 squared plus f2 squared plus f3 squared plus f4 squared plus f5 squared. That's equal to 1 squared plus 1 squared plus 2 squared plus 3 squared plus 5 squared. Okay, we've already added up the first four squares of these terms. Up here, that was 15. 5 squared is equal to 25, and 15 plus 25 is equal to 40. Now, what is the fifth and sixth? What are the fifth and sixth terms of our sequence? 5 and 8, and 5 times 8 is also 40. That equals 5 times 8, which is f5 times f6. So this is what that property is up here. The sum of the first n squares of the terms of the Fibonacci sequence always equal the product of the nth term times the term that comes after it. So is this a particularly useful property? Maybe, maybe not. But again, sort of one of the underlying themes throughout Chapter 5 that we've talked about is that even though, you know, a lot of number theory does have practical purposes, a lot of it is just kind of interesting curiosities about the natural numbers and just patterns that exist, whether or not we can use them for anything, in kind of the real world, I guess. All right, so we've looked at the Fibonacci sequence. Now we want to talk about another pattern that emerges, and this is going to take us into this thing called the golden ratio. So if you were to take pairs of consecutive terms in the Fibonacci sequence and divide the latter term by the former term, creating ratios. So 1 divided by 1, 2 divided by 1, 3 divided by 2, 5 divided by 3, 8 divided by 5, and keep generating ratios that way. Then the ratios, if you were to plug them into a calculator and get a decimal approximation, seem to be approaching some specific number. They don't seem to be jumping around all over the place. So here it is, 1 divided by 1 is 1, 2 divided by 1 is 2, 3 divided by 2 is 1.5, 5 divided by 3 is 1.666, repeating. And then you kind of continue onwards, and this is just continuing this pattern all the way down the Fibonacci sequence. And we seem to be approaching some number, 1.618055556. It seems to be kind of approaching some number around this one right here. In calculus, we talk about this. We call this a limit. So this sequence of numbers that we're creating right here out of these ratios has what's called a limit, a number that those ratios are getting arbitrarily close to. And we can show, even though we're not going to do it here, we can show that this ratio, or this limit, this value that this thing is approaching, is exactly equal to 1 plus root 5 over 2. Again, this may seem like it's coming out of nowhere, but we can use techniques that we don't really assume you guys have as a background in this class to prove that. This number, 1 plus root 5 over 2, we call this the golden ratio. And we denote it by the Greek letter phi, which is this symbol right here. The golden ratio was an object of interest, or a number of interests dating all the way back to the ancient Greeks. And it turns out that it appears in a number of interesting places throughout nature, throughout art. It sort of, in some respects, it encapsulates like what some people consider to be perfect symmetry. And we can't dig that deep into this without a little bit more math, but we will talk about its relationship to something else that the Greeks looked at, which is called the golden rectangle. So let's talk about that next. What is the golden rectangle? Well, the golden rectangle, or a golden rectangle, is a rectangle with very specific dimensions. Imagine that we have this large rectangle right here. Okay, and it's not a square, so it has a longer side and a shorter side. Now, if you take the shorter side of that rectangle and use it to measure out part of the larger side. So, for example, I'm calling this shorter side L right here. Because L is shorter than this longer side of this rectangle right here, it's going to only make up part of that longer side. Then the remaining side, whatever's left after drawing L here, I'm going to call that W. And these two lengths together subdivide this rectangle into two parts. So L is the length of this side, but it's also the length of this side, which creates a square down here. And then this remaining part of our rectangle is just a smaller rectangle than we started with. Okay, now we call this larger rectangle a golden rectangle if, after you've subdivided it in this way, if the smaller rectangle is proportional to the larger rectangle. You talk about proportions a lot in previous math classes, pre-algebra and algebra, we deal with them a lot. Basically, all that means is that their sides are in proportion to each other. And a way of checking that is if I took the longer side and divided it by the shorter side of the smaller rectangle. And then if I took the longer side and divided it by the shorter side of the bigger rectangle, those two quotients should be equal to each other. Those two ratios should be equal to each other. Same thing if I did it the other way around. If I did short side divided by long side of the big rectangle, short side divided by long side of the small rectangle, those two quotients should give me the same number. We would say then that those rectangles are proportional to each other. So a golden rectangle has that property. Now, let's think about that property from an algebraic perspective. That Greek letter phi that I talked about, I'm going to set that equal to L over W. We're going to show that that this is going to create the golden ratio. That's why we're using this symbol right here. So if I set up those proportions, L over W, L divided by W is the longer side divided by the shorter side of the smaller rectangle. That property that I talked about states that L over W should be equal to the longer side of the big rectangle divided by its shorter side. But the longer side is the sum of L and W. That makes L plus W there. The shorter side is just L. We can see that up here. So that's the second ratio, and because those two things are proportional, we can set those ratios equal to each other. Okay, now this second ratio over here looks like a sum of two terms over a single denominator, and you can split that up into a sum of two rational expressions, L over L plus W over L, which is what we have down here. L over L, of course, is equal to 1 because it's dividing a number by itself. L over W, the thing I'm seeing on the left-hand side, I gave a name to that. I'm calling that phi. Okay, so I can call this thing phi. Now on the right-hand side, W over L, this other term here, is the reciprocal of this term. L over W, W over L. And one way of representing a reciprocal of a number is to write 1 over that number. So if we're calling L over W phi, then W over L is the same thing as 1 over phi. This is the reciprocal of this. Now what we're going to do is treat this like an equation that we want to solve from algebra. So the first thing you do in a case like this is you clear the denominator. I have a phi in the denominator here, so if I multiply both sides of this equation by phi, I'm going to get phi squared on the left. 1 times phi is phi, and then multiplying 1 over phi by phi, those just cancel, and I get a 1. Phi squared equals phi plus 1. Then if I subtract all of these terms to the left-hand side, I get phi squared minus phi minus 1 equals 0. We've created a quadratic equation out of this. And from algebra, you've had lots and lots and lots of practice solving quadratic equations, so this should be no problem. This does not factor nicely, so we resort to the quadratic formula in order to solve this. Okay, so here's what the quadratic formula would look like for that quadratic equation that we just found. Phi equals, remember this, negative b plus or minus the square root of b squared minus 4ac all over 2a. And in this case, we get 1 plus or minus the square root of 5 over 2. Now that's two solutions. Remember the quadratic formula, unless your discriminant, this thing under the radical, is equal to 0, will always give you two solutions. However, one of these solutions is negative. The square root of 5 is larger than 1, and so if I did 1 minus root 5, I'd get a negative number over a positive number, which is negative. However, the way that we defined phi implied that it should never be negative, because remember, phi is the quotient of L and W. L and W are both dimensions of a rectangle. Those have to be positive numbers, and so their quotient has to be positive. What does that mean for us? Well, it means that even though we ended up with two solutions here, one of them is invalid in the context of where L and W came from. So we throw that one out, and that means the only solution that works for our golden rectangle here is 1 plus the square root of 5 over 2, which is exactly the golden ratio that we talked about in the Fibonacci sequence. Okay, so the golden rectangle makes an appearance here as well. To wrap this section up, we're going to take that idea of the golden rectangle in the Fibonacci sequence and use it to create something that's called a golden spiral. So this is a really interesting application of this, and this is where we see this show up in nature a lot. So you should be familiar with a spiral, a shape that's similar to this. But the golden spiral is a spiral with very specific dimensions. It unravels in a very specific way. And spirals that have these kinds of proportions show up all over the place in the natural world. Your book shows you an example of a cross-section of a nautilus shell. Nautilus is it's a shell, like a seashell. It has this exact shape to it. So what we do is we construct a golden rectangle with dimensions 89 by 55. That's what we're seeing here. Notice 55 plus 34 is 89. Okay? We can show that this would create a golden rectangle. It would satisfy that property that we talked about for golden rectangles. Now, the rectangle, after doing our subdividing of it, would look like this square right here, this 55 by 55 square, and this rectangle down here. But another property of golden rectangles is that once you get that smaller rectangle, you can repeat that subdividing process to create another golden rectangle out of the smaller rectangle that's going to appear. And you can see that you can keep repeating that and create this sort of infinite sequence of golden rectangles sort of collapsing in on themselves here. Okay? If I were to do that, so if I were to create those golden rectangles, I'd have this 55 by 55 square here, a 34 by 34 square here. And then if you look at the smaller square that's going to be created by this next subdivision, it's 21 by 21. Then we're going to get a 13 by 13 square here, and then an 8 by 8 square here. Those numbers should look familiar. Those are terms in the Fibonacci sequence. So the dimensions of this rectangle this rectangle that we're creating, automatically creates the terms of the Fibonacci sequence as it sort of pairs down to this, ever decreasing in size golden rectangle down here. Now, if you've constructed this thing with these, smaller rectangles, and create a spiral that goes through the diagonals of all the squares that you've created. So this is going through this corner and this opposite corner of this 55 by 55 square, and then this 34 by 34 square, and then this 21 by 21 square, and then this 13 by 13 square, and then the 8 by 8 square, and this actually continues. This next would be a 5 by 5 square, and so on. The spiral that creates is called the golden spiral. And again, like I said before, that spiral has proportions that show up in nature a lot. Okay? That's it for section 5.5. Like I said, it's a short section. This is more, I would call this more of an appreciation section, kind of just learning an interesting thing without asking you to do a whole lot with it, even though there is homework for this section. But that's going to wrap up chapter 5 for us.